let's imagine that I have an entire set of wave functions that span the entire space that I'm looking for. So we said earlier, for example, when you have an operator that represents an observable, so if I have A, we said that this has a set of eigenvalues and a set of eigenvectors here. And this is, so we have, these were the eigenvalues, and these one up here are the eigenvectors. So imagine that we take all the eigenvectors of A that we know, and we look for, or we calculate the following elements. So we're going to take the eigenvectors um, A, un. Or if you wish, if you don't want m and n, we could do this with I and j maybe, so that it maybe makes it a little bit easier. So we could go like this. I could erase this and go with I and j. This is just picking some values from the, any eigenvectors. There's a whole set. I'm picking two of these eigenvectors, I and j. So of course there's going to be two things. One, in one case, either I is the same as j or I is different from j. But the main thing that I want to show you here is, we know that this represents an integral, and we also know that because it represents an integral, this is really going to give you a number, a scalar. So this will give you a number, or scalar, for each I and j. For each combination of I and j that you have, you get a number. So if you were to represent all of these results, what you would have is, if I had, and you might be able to see where I'm going with this, if I have all the I vector here and all the j vector there, I would have a value for this, another value for a slightly different vector, and a value for that, and a value for that. And probably because the I and j will be the same, if I swap I and j, I'll get very likely the same value here, same value there, same value here, and then for that one I'll get maybe something different, etc, etc, etc. I can see that. So what I can do is, by using this operation, I can essentially build a matrix representation of A in the basis of its eigenvectors, or in the basis of any vectors that I want. As long as it's a complete basis, I will obtain a complete representation of A. So this is a matrix representation of A in the UI or UJ or UN, I suppose, basis. And if you think about it, and if you've worked a little bit with matrices before, this is exactly the same thing as saying, oh, I'm looking at how I can represent a particular matrix on a basis of vectors, and this is essentially what you end up with. So that works really well. we can probably go one step further with this, which is because we said these will be the eigenvalues, in fact, we know what the values of all these things are, because these are, sorry, the eigenvectors. If I do this operation, if I apply the operator A to uj, we know what this is going to give me. It's going to give me aj times uj. Why? Simply because uj is an eigenvector of A, and the eigenvalue that comes out of this operation has to be the corresponding eigenvalue, which is aj. So if I do this and aj is a scalar, what happens is when I calculate ui a uj, this is actually the same, see if I was to put brackets here, the same as calculating ui aj uj. It's the same thing, but aj is essentially a scalar, a number, the same way as when we had just a value of 1. So this is actually equal to aj ui uj. Oops. And once we have this, we say, oh, okay, so this is really just the overlap or the integral between a vector uj and a vector ui, but we know that these are eigenvectors, so they are orthogonal to each other by construction, and they are normalized again by construction. Therefore, this is really, we can use this to work out what the values are. These will be aj times delta ij, which means when I and j are the same, this is ai or aj because they're the same, and where I and j are different, then these entire rows here, this whole section and that whole section, will be 0. So we actually now found out that if you use your eigenvectors to represent your matrix, you will obtain a diagonal matrix where all the values along the diagonal will be your eigenvalues and all the rest will be 0. We will come back to this and we will show maybe more formally how we can do that when we actually apply this to operators, and how we actually go and look at decomposing an operator onto vectors. But for now, what I'm going to do is I'm just going to finish this by quickly summarizing some of the properties or some of the things that we have in Dirac notation. So to summarize, what have we got? We know that a function that is a complex conjugate corresponds to a bra, that we write like this. This is a bra. We know that the same function that isn't complex conjugate corresponds to this, which is a ket. We can sandwich operators between bra and ket to represent an integral, and therefore we get a number. And these will look like this, where we'd have the other thing that we know is that if A is a number, or also known as a scalar. The number can be taken out of the bracket. And if that looks weird to you, just think about what you would do with an integral. If you have an integral between two functions and there's a number in between, you can take the number to the front. You'll take it out of the integral because you say, well, that's just going to be so many times the value of that integral. So it sort of works out the same. And we can then, I think that's pretty much all there is that we've found. I think the other thing that maybe is worth noting is if you take the complex conjugate of a bra, that's equal to this, and the same goes the other way around. If you get the complex conjugate of a ket, that is oh, I've written the same thing, sorry. So if you take complex conjugate of a bra, you get a ket, and if you get the complex conjugate of a ket, this is going to be a bra. And that's it. We will get more, you will get more familiar with this as we go along, as we'll use things, and when we do demonstrations I will point out all the various things that happen with Dirac notations. But essentially the main thing to remember is that you have bras and kets. These are vectors, and the reason why they are like this, so these are what we would call vectors. These are vectors, and the main reason why we have bras and kets is because in quantum mechanics you can have complex wave functions, so a bra and a ket are not the same thing, but you can transform between them using the complex conjugation operation. We can use that to represent integrals, so anything that is sandwiched between a bra and a ket represents an integral, and that's a number. And if your operator is just a single number, then like you would in an integral, you can take this number out of the bracket and then just look at the bracket itself. And that's it. So hopefully this helps you understand Dirac notation. We'll do lots of practice of it, but trust me, it is actually a lot easier and a lot simpler than just writing loads and loads and loads of integrals. Okay, bye.